Hi there, here we are again. Last time we looked at the distribution of a sample mean, and we said that if the sample size is big enough, that the distribution of possible sample means, so if I took a bunch of samples of the same size, then the distribution of all those different means that I would get from those different samples is approximately normal. And now we're going to say, well, what if I don't know the mean of the population? Right? So that's what this is all about today. All right, so again, here are my guided notes. Let's see, did I actually share that? There we go. All right, here are my guided notes that you can print out from the website. So let's get started. All right. So generally we don't know what mu, the population mean, is. So what do we got? Here's the situation. We've got this population, and this is everybody. You know, all the men, all the women, all the students, all US Americans, all right? And there's some mu here. This is a parameter mu, all right? This is the mean of the population, and I don't know what that is, all right? So this is generally in statistics, when we're actually practicing statistics, this is the thing. I want to know what this mean is. So how do I find this out? I take a sample, all right? So I sample from this population. Nice circle, huh? Sample. All right. And this is going to be the N, N whatevers, the N men, the N women, the N students, the N Americans, right? And inside here, we can calculate some stats. So from here, we can get stats, statistics, which are, remember those, what's a statistic? It's a calculation from data. All right, so this is my data, all right? And I'm going to have N, which is the sample size, Y bar, this is the sample mean. All right, so the mean of my sample, and S, which is the sample standard deviation. All right, so then this mean of my sample should be close to this mu, the mean of the population, what I'm interested in, all right? So I can use this as my estimate, plus or minus some margin of error, right? So mu, I think, is going to be Y bar plus or minus some margin of error, right? This plus or minus, so it's going to be close to Y bar, but how close? That's that margin of error. And here is our formula for that. So our confidence interval for mu, we take the sample mean, I'm going to add and subtract. Now we had a Z star before, we're going to have a T star this time. And we have our standard error. And our standard error here is S over the square root of N. So there's my formula, and we're going to go through why does my formula look like that. All right. So we'll start here with what we know. All right. So what we know is that if we knew mu and sigma, which we don't, all right, we expect 95% of the Y bars to be within 2 standard deviations of the mean. All right. So we learned last time that Y bar, if the sample's big enough, is approximately normal with mean mu and standard deviation sigma over the square root of N. All right. So 95% of the time, our Y bars will be within 2 of these of mu. All right. So that's what this graph is. I've got mu, add 1 standard deviation, add 2 standard deviations. Subtract 1, subtract 2. So 95%, there's going to be 95% in this range here. So 95% of what? Sample means, all right? So this, again, is if I were to take many samples. That's what this is. So if I took many samples of the same size, all right, 95% of the means that I get from those samples would be somewhere in here, all right? So 95% of my Y bars would be in this range, all right? And then 5% of the time, I either be bigger than this, my y bar would be out here, or my y bar would be out there. All right. So basically, so in 95% of samples, y bar is in the interval mu minus 2 standard deviations, which is sigma over the square root of n, and mu plus 2 standard deviations. Okay, so if y bar happens to be in here, which is going to happen 95% of the time, then so if y bar is within 2 standard deviations of mu, then mu is also within 2 standard deviations of y bar. So basically, if my y bar happened to be in here, let's just say it happens to be right here. Let's say y bar is here. It's on this, close to this edge. But if I add 2 standard deviations to this guy, right, and I subtract 2 on the other side, all right, so here's this guy. This interval, if you look, mu is in it. So if y bar is on this edge, mu is going to be in this edge. So basically, in 95% of samples, y bar is going to be in this interval, but mu, which is what I don't know and what I'm interested in, is going to be, so in mu is in this interval, y bar minus 2 standard deviations, which is standard deviation again, is sigma over the square root of n, and y bar plus 2. All right, so if I knew sigma, then I could use this as my interval, my confidence interval, just take the mean that I got from my sample, get this guy, and add a couple standard deviations. But here's the deal, I don't know sigma either. And I use S, the sample standard deviation, as my estimate of sigma, the population distribution, but that is going to change things. All right, here's where we're going to talk about that. All right, so what I'm going to do is I'm going to say, okay, you know, I want to use this interval. I want to say, you know, a confidence interval for mu, I could take y bar and add or subtract 2 sigma over the square root of n, all right, which is basically just rewriting this, all right? But I don't know sigma. So what I'm going to do is I'm going to take S, and I'm going to use that. My sample standard deviation is a good estimate of sigma. So I'm going to stick that in there. And so that would be my standard deviation, except there's a problem. When I substitute S for sigma, when I use the sample standard deviation instead of the population distribution, it changes things. I no longer have a normal distribution, all right? So if I take y bar, I value y bar, and I subtract the mean, the population mean, mu, and divide by the standard deviation, sigma over the square root of n, that's a z-score for some y bar. And that has a standard normal distribution, and we could go to the z table for that, all right? But when I change the sigma here, and I replace it with S, all right, because S is going to be spread out, right? S is not going to equal mu. It's going to be close to mu. So it might be a little bigger, a little smaller. Then I get a different distribution. I get a more spread out distribution. All right, so this T distribution, this is more spread out than a Z, right? And that's called, we call it the T distribution. And it has a parameter, it has n-1 degrees of freedom, all right? So here you can see, I've got 2 graphs, and it says the black line is the T. So so you can see the T where it has values farther out in the tail than the blue line, which is the normal. So you can see the normal, you see this little blue right in here, that's the normal. So 95% of the time, we're within 1.96 standard deviations, all right? So this is, but for the T, we have to go farther out, all right? So in order to have 95% in here, it's got fatter tails. I have to go farther out. So to be within 95% of the mean, I have to go out. For instance, if this has 4 degrees of freedom, so this is a T with a T distribution with 4 degrees of freedom. I'd have to go out, instead of 1.96, which is my Z star, my T star would be 2.78. And that's for 95% confidence. All right. So my T's are going to be bigger, my T stars are going to be bigger than Z stars. All right. So as we go out, we get bigger T stars. And then basically, the bigger my sample size is, then the closer, so a large sample, this S, the standard deviation of my sample from a large sample, is going to be a lot closer to sigma. So what's going to happen is, as my degrees of freedom get bigger, the T gets closer and closer to the normal distribution. Okay, so I have what's called a T table. So here is just part of it. It's a little bigger. Okay. So here's part of the T table. And so it has the degrees of freedom. There's my 4. And here is for 95% confidence, our T star is 2.78. So that's where I got that. I had 4 degrees of freedom and 95% confidence. So that's where that 2.78. So this table, this T table, these are all T stars. All of these, all right? And so basically, for a sample of 5, all right, so if n is 5, I take a sample of 5 people, then my degrees of freedom are n minus 1 equals 4 degrees of freedom, all right? Then these are all the T stars, these 1, 2, 3, 4, 5, these are all the T stars for this particular distribution, for this particular T. And so 1.533, that would be the T star if I was doing an 80% confidence interval. And 2.132 would be for a 90%. And then if I really want to be, really sure that mu is in that interval, then I might use this 4.604. So you can see the confidence levels are at the bottom of the table. The rows are the degrees of freedom. All right. So if let me move down a little bit. Right. So if my sample size, had 41 people in it, right? Then my degrees of freedom is 40, and then I would go to row 40 for my T star. All right, so I go here, I'd say, okay, here's my possible T star. And depending on the confidence level, like the middle column is for 95%, the last column is for 99%, then I would pull that as my T star. All right. Let's say that n had 45 people in it. All right, so my degrees of freedom are 44. All right, and I go to the table. Well, there's not a 44. All right, I have a row for 40 degrees of freedom, and I have a row for 45 degrees of freedom. No 44. So what I just use the row closest. All right, so here I would use row 45 because so 45 degrees of freedom is closer to 44 than 40. And so then I would use the second set for a sample size of 45. All right, so let's do an example. All right. And here's my formula. All right, so I'm going to have, so my confidence interval, my formula for that for mu, it's going to be my sample mean plus or minus my T star, and this guy has n minus 1 degrees of freedom times S over the square root of n. All right, recall the standard deviation of y bar. This was sigma over the square root of n. All right, and when I replace that with S, so I just make this guy an S, then what happens is this is my estimate of that standard deviation, and we call that the standard error. All right, so this is the standard error. This whole thing on to the right, you remember what that's called? The plus or minus part? That is called the margin of error. All right, that's the amount that you add and subtract from y bar. That's how close I think y bar is to mu with my given confidence level. Okay, so now the example. Let's say we have a car owner. Her mileage she takes once a month for 3 years, and she gets so she calculates her mileage. The way she would do that is she say, okay, miles per gallon, so that's miles divided by gallons, so how many miles she traveled over the gallons of gas she used. And the mean mileage for those 36 months, this is y bar, all right, 3 years monthly, tells me that I've got an n of 36 months. Y bar, that's my average gas mileage, right? And the standard deviation was 1.44, right? So the reason this is not mu and sigma is because these are measuring the sample of 36 months. So these are sample statistics, so I use y bar and S, not mu and sigma, which I would use if I was looking at overall mileage. And that's what this is saying. What is a 95% confidence interval for overall mean mileage? Right? So what kind of average if she was to do this for all months and all time? And that is going to be mu. All right? So we want a confidence interval for mu. So my formula for that is y bar plus or minus T star n minus 1, just like I have up there, times S over the square root of n. All right, so we got y bar, 25.95. We got S, 1.44. And we got n, 36. And we just need this T star. So we need a T star. So a T star with n minus 1 degrees of freedom, so that's going to be 35 degrees of freedom, all right? And we want a 95% confidence interval. All right, let's go back up to our table here, and what do we say? 35 degrees of freedom, n minus 1. So 35, 95%, that's going to be this guy, 2.030. All right, so I calculate that. Which I already did for us, and that number is 0.49. All right, so I took 2.03 times 1.44 divided by the square root of 36, and that's my margin of error. By the way, this whole thing right here, that's the standard error. For the standard error, this is going to be 1.44, the square root of 36, we happen to have an even square there, over 6, and this is actually 0.24 miles per gallon. So this is my estimate of how spread out her mileages are month to month. All right. So now I'm going to, so my confidence interval is going to be 25.95 minus 0.49 to 25.95 plus 0.49. And that ends up being 25.46 to 26.44. So let's interpret this interval. All right, so we were looking for her overall mean mileage. That's what this confidence interval is for. All right, so we always start our interpretations of confidence intervals should always mention a few things: a confidence level, which here is 95%, and we should mention a population parameter. All right, so both of those things. So I should mention the population here is overall, like her lifetime in this car, all right? And the parameter here is the mean mileage, all right? So that's what we're gonna do. So we're gonna mention the confidence level, we'll just start with however much confidence. This was a 95% confidence interval. So with 95% confidence, all right? And then now we're gonna talk about something being between these two values. So it's gonna be the parameter. So her overall mean mileage is between let's say around this to 25 and 26 miles per gallon. Right. Okay, so sometimes we can do a test using a confidence interval. All right, so let's ask this question: does the interval support the idea that her car gets over 25 miles per gallon? All right, so let's go back and look at her interval. So we said it's between 25 and 26, but we should probably get the values. All right, so we're 95% confident that her car gets between 25 and a half and 26.4 miles per gallon. All right. So does that mean we're confident it's over 25? Well, yes, because we're confident because this whole interval, the entire interval is over 25, right? So the answer to this question is going to be yes. And why? Since the entire interval and those are of plausible values for the mean, are over 25 miles per gallon. All right, so since the whole interval is that way, then we know that. Well, what if I said, does this interval support, all right? So what if we said, all right, does her car get less than 26 miles per gallon? It'll be a weird question to ask, but hey, all right. So we go here and we go back up and look at the interval. All right, it's between 25 and a half and 26.44. So do I have strong evidence that it's less than 26, right? And here's the deal. The interval goes between 25 and a half and 26.44. So there's between 26 and 26.44, which is bigger than 26, are plausible values. So we're not sure, right? All right, so we're going to say, let's just say not necessarily. All right. Okay. It could get over. It could reasonably get, right? Because this is on our 95% B. All right, between 26 and 26.44 miles per gallon, which is over 26 miles per gallon, all right? So it doesn't suggest that, all right? Okay. What if I wanted to do this in StatCrunch, all right, which we can do. So in StatCrunch, if you have summary information, all right, we're going to click T-stats, one sample with summary. So let's open up StatCrunch. Let's, no, this is for a later exam, but we can do it. So we're going to do T-stats, one sample with summary. And here we would put that sample mean in there. So the sample mean, so for the 36 months, the average mileage was 25.95. And her standard deviation was, let me go back. 1.44 miles per gallon, all right, of those 36 months, all right? And I want a confidence interval. So I click on that little confidence interval guy. And that's all I needed to do. And if I had wanted a 99% confidence interval, I just change this to 0.99. But I don't, I want a 95%. So I'm gonna hit compute. And so here's my 25.46, 26.44 miles per gallon. All right, for my upper and lower limit of what I think mu is. All right, so I think the population mean is somewhere in this interval right here. You see there's my degrees of freedom, 36 minus 1, and there's my standard error, which was that S, which was 1.44 over the square root of 36. So that's where that guy comes in. Okay. All right, so now we have how to get the interval, all right? But we didn't talk about the conditions, all right? So for every confidence interval or test, we always have the independence of randomization condition. So basically what we want a good sample. And so basically I want that sample, a good sample, it's going to look like the population. All right, and I can get that by either taking a random sample, or if I don't use randomization, I still need to try to come up with a good sample. I want to have, n, let's say 50 people or things that I believe represent the population. So I want n, and they should be independent of each other, which means they're unrelated to each other. They shouldn't affect each other's value. N independent observations that we believe represent the population. This should not be new information. This is, we've been talking about this with when we did tests for populations or for proportions. So looks like the population. So I'm hoping that's the case. So I can do that with a random sample or just by, trying to make sure I get everybody represented in the population. All right. The other condition, which is different for proportions. In proportions, we had successes and failures. All right. Because it was categorical, we said one category was a success, one was a failure. But here we don't have categories, we have amounts. So it's different. So basically it has to do with that central limit theorem where we talked about that if our sample's big enough, then the distribution of the mean is normal. All right. So how big does it have to be? Well, it depends on how close to normal the distribution is to start with. So what we do is we get a histogram of the data, and if it's a small sample. So if we have a small sample, let's say n less than 15, all right, the histogram should be nearly normal to begin with. So maybe I have something like this. All right. So if if n is less than 15, I want something like this. It needs to be unimodal and almost symmetric. I might even have one of these. That might be good too. All right. So as long as it's not skewed, we've got big gaps, nothing like that. As long as it doesn't have way more bars on the right side than on the left side, then we're pretty good. All right. Now let's say it's between 15 and 40. All right. So that's a moderate sample. This is called a small sample. Well, this one, if it's bigger sample, then we have more of a chance to get the mean looking normal. All right. So if it's skewed, as long as it's only slightly skewed, it's good. So maybe it might be, maybe I got 1 bar over here and maybe 3 bars over here, you know, something like this. This is okay. All right. So this is between 15 and 40. So this is moderate. So as long as it looks something like that, we're good. Now, if it's very skewed, then it doesn't meet it. All right. Now, if n is greater than 40, all right, so here's n is greater than 40. This is a large sample. It's not really that large, but it's considered a large sample because usually, even if it's pretty skewed, a sample size of 40 will have y bar be normal. All right. So this could be, you know, I could have something that's pretty skewed, but it just cannot be extremely skewed. So I might even have something like this. No extreme outlier. So this is fine. All right, so this is right skewed. This we said this is slightly right skewed, which is fine. And this is just right skewed. Right? But in order for it to qualify, it can't be extremely skewed. Right? So again, for small samples, it should be nearly normal, which means unimodal, almost symmetric. Moderate samples, at most slightly skewed. So it's okay if it looks like this. If it looks symmetric, that's still fine, but it can't be very skewed. Like it can't be this far out. All right. And as long as it's for big samples, as long as it's not extremely skewed, as long as it doesn't look like, remember our CEO example? In our CEO example, it was crazy skewed. It looked something like, you know, had almost a bunch of things here, and then it had all these little, I mean, way out there. It's off the screen. So this was the CEO thing. Yeah, that's no good. All right. So this one, we can't do a confidence interval for this guy. All right. So we're only going to handle things that are unimodal. So all of these have to be unimodal. All right, so they have to be unimodal, and depending on the size, we can have a little bit more skewness. All right, let's do an example. All right, so in the study of the breakdown of bone, we have 31 women, that's my N, submitted blood tests, and the mean OC, which is called osteocalcin, was 36.2 nanograms per milliliter, I'm guessing. All right, so this mean OC, is this mu or y bar? And how do I know? All right, I know you can't answer, but all right. So this is a mean. That means it's either y bar or mu, right? Y bar measures a sample, and a sample are the observation we have data for, and that's what we have here. We have 31 women. That's my sample who submitted blood test, and so this mean is measuring those 31 women. So that makes this guy y bar. So I had a mean, so of those 31 women, their mean osteocalcin was 36.2 and the standard deviation was 21. Again, this is a sample standard deviation, so that's S. And so here's my data. So I'm going to check my conditions. The first condition is the randomization or independence. All right, and to figure out if it meets that, I have to look and see how the data was collected. And it doesn't tell me. All right, so basically, since it doesn't say whether or not it was a random sample or they were independent women or I got them from different hospitals or different, you know, I don't know if this condition is passed. The condition is met. I need some more info. How did they get these 31 women? All right. We're going to do it anyway, even though we don't know. We're just, you know, maybe if I was publishing something, I would say, you know, consider that we're not sure how the data was collected. There could be bias. All right. So the second condition, now we're talking about that size condition or the almost normal condition. All right. So my sample size is 31. All right. So we got to go back up and say, all right, well, how big is that sample? So 31, that's between 15 and 40. So this is a moderate sample. And that means that my histogram should be most slightly skewed. All right. So we're going to say N is 31. All right. So my condition is that the histogram should be at most slightly skewed. All right. So I got to go to the histogram. Here's my histogram. Is it at most slightly skewed? Yeah, I've got like 3 bars to the right, 1 bar to the left. It's only a couple extra bars, so yes. All right. So that means this condition's met. If this was my sample of 31 women, then this sample would be big enough that the sample mean, if I was to take many samples of 31, the average of those samples would be normal. All right. So that means I can do my confidence interval. So now I'm going to do my confidence. Oops. Okay. A little too far there. All right. Okay, so let's do my calculations. So my calculations are, so my confidence interval for mu, this is y bar plus or minus t star n minus 1 degrees of freedom times s over the square root of n. All right, so here's y bar, s, and n. We said was 31, so I got that. So I need my t star. So my t star, all right, n minus 1 is 30 for 30 degrees of freedom, and oh, I didn't say. All right, let's do a 99% one. All right. I'll make us 99. I didn't say in the example. I'll just make it a 99%. So I need a T star for 30 and 99% confidence. All right, so let's go back up here. All right, so to my T table that I had an example of. By the way, the T table, you can print that from the home screen or even just download it and look at it. So I've got 30 degrees of freedom. I want a 99% confidence interval. All right, so here's 99%. Here's 30 degrees of freedom. So my T star is 2.75. Okay, so now I have everything I need for this interval. Y bar, this was 36.2, plus or minus T star, that's we said was 2.75, and S was 21, and the sample size was 31. All right. Okay, so here we go. We got 21 divided by the square root of 31. All right, and that is 3.772. All right, and then I'm going to take that times 2.75. So about 3772, that's my standard error. This is my T star, and I'm going to multiply it times that, and I get 10.37. And actually, since this is in one decimal place, I'm going to keep this one in one decimal place. So this is 10.4. This is 36.2, 36.2. Those 36.2 plus or minus 10.4. And so, so that'll be, so my interval is going to be 36.2 minus 10.4 and 36.2 plus 10.4. All right, so subtract 10, that gives me 26. And then that'll, so it's another 0.4, that'll be 25.8. And we got 36.2 to 10.4. That is going to be, add 10, that'll be 46. And then 2 and 4 is 6. And this is in, like I said, I think it's nanograms per milliliter. I'm just guessing. All right, so there's my confidence interval. So what's the interpretation? All right, so this, again, we're going to mention those 2 or 3 things where you can look at it. I have to mention my confidence level and the population and the parameter. All right, the parameter here is mu, the mean. The population, let's say this is all similar women, all right? Because I've got these 31 women. I don't know what they look like. So we'll say women like them, all right? And then the level of confidence, we said this was 99%. So with 99% confidence, the mean, that's mu, the mean osteocalcin for, let's say, women such as these is between, and again, I'm going to round to the whole numbers, this is between 26 and 47 nanograms per milliliter. Okay, so that's where we think mu is. Now, the reason we got to mention this confidence, we're not sure it's in there. We're just pretty sure it's in there. We're 99% confident that the average for all these women is in this interval. All right. Okay. Now we're going to use one with data. All right. So I have a data file of late arrivals for flights in percent. All right. So let's go to, there we go. Okay, get rid of this. All right, so here's, so this is by month. So that's why there's 12 late arrival percentages for 95. So over several years. And we want to do a confidence interval for what percent of flights are late. Okay. So in order to do that, let's go back to my notes. Before we do that, we should check the conditions. All right. The first one is randomization or independence. All right. So this is, it's for 193 months in a row. So the question we got to answer ourselves, are these many months, are they representative of late flight times in general? You know, is there any reason for flights, more flights to be late or less flights to be late in other months outside of this? And I would say no, other than if you're, the big change with the coronavirus, maybe things have changed, but we're going to just say, let's say if there was no coronavirus, which could obviously create a different kind of percentage, if there wasn't anything crazier than happening, that these months would be representative of all months, all right? And the independence is the percent of late flights for January independent of late flights for February. And I would say yes, that they're not related to each other. So I'm going to say, yes, this is met. We got a good sample. All right. The second condition is the size condition. All right. So we have a very large sample. It's 193 months. All right. So in order to check that condition, I need a histogram. All right. I have to see, is it extremely skewed? Does it have extreme outliers? So we're going to look at the histogram. We're going to draw one in StatCrunch. And we're going to ask ourselves, is it unimodal and not extremely skewed? All right. And no extreme outliers. So we can't have any extremeness in it. If it's extreme, then we can't do the confidence interval. All right, so let's go see that. Get back to my StatCrunch here. All right, so we're going to do a histogram. That one's easy. Graph histogram. All right, so I'm going to look at late arrival percent. And I get this histogram. Unimodal, almost metric. All right, so this is almost normal. That looks right. No extremeness, so it meets the condition. All right. Back. Looks great. So the histogram is actually, this was my question. Is it this way? And in actuality, it was unimodal symmetric. So that meets that condition. All right. So now we're going to do the calculations, and we will do that with StatCrunch. All right. We're going to click stat, t-stats, one sample. This time I have a data file. I have one row per percent. And so I'm going to do it that way. So let's look. All right, so we got stats, t-stats, one sample with data, because I have that data, that column late arrival percent. All right, and I'm going to pick that guy. And then I'm going to go down here and I'm going to say I want a confidence interval. And let me see here. And we wanted a 99% one. So I'm going to change this guy to 99. I hit compute. And there's my confidence interval. So there's my standard error. That was the S over square root of N. So on average, 20.4% were late. And I add a couple standard errors. And so I'm 99% confident that I'm between 19.56 and 21.15. All right. Okay, so we had that the confidence interval was 19.6 to 21.2%. Right, and that the actual mean, my Y bar, this guy was 20.4%. All right, so on average for these 193 months, it was 20.4%. And so we take 20.4% plus or minus my margin of error. So this, I'm 99% confident, which means I'm pretty darn confident that the mean arrival time is in there. So that's what I'm going to do. So here, again, I'm going to mention my confidence level with 99% confidence. The mean late arrival percentage, late arrival rate, is between 20 and 21%. Now, I rounded in my examples to whole numbers, but you round on your homework to whatever it tells you to. It likes a lot of decimal places. So that's what you're going to do. All right. And that is all I have for today. And I hope you guys are enjoying your time at home, which you probably are not. You're probably bored stiff, but just try to keep up your spirits. It's only a few weeks. We'll be fine. All right. Have a good day.